In this video, we will focus on nucleophilic addition by enolates, and we'll look first at the aldol addition and aldol condensation. Before we get into the details of nucleophilic addition by enolates, let's first review what we've seen about nucleophilic addition. So in general, if we have an aldehyde or a ketone, a nucleophile can share its electrons with the carbonyl carbon, pushing these electrons up onto the oxygen, which gives as an intermediate something that looks like this, where there is a new bond between whatever the nucleophilic atom is and the carbon that used to be the carbonyl carbon. From this intermediate, the O- might be able to grab an H+, giving us the new alcohol. And again, the nucleophile is connected to what used to be the carbonyl carbon. For some reactions, this is the end. For others, once this is formed, additional reactions are going to happen. But the important common feature is the nucleophile adding to the carbon, forming this intermediate, followed by this product or intermediate. Let's look at some specifics. The first type that we saw was reaction of a Grignard reagent, where the R group would add to the carbonyl carbon, push these electrons up, and we would get an intermediate that looked like this, where this is the new R group that added from the Grignard. And then on aqueous acid workup, the O- would be protonated to give an alcohol and with a new R group. Another example that we saw was using something like cyanide. So cyanide can act as a nucleophile, share its electrons with the carbon, push those electrons up onto the oxygen, giving us this intermediate. And then aqueous acid, the O- can grab a proton. And so what we formed here was called a cyanohydrin. Another reaction that we saw involved reaction with two equivalents of alcohol in the presence of acid, for example. This would lead to this intermediate, but then this would react further with the second equivalent of the alcohol to give this, which is an acetal. Remember when we used an amine, whether it was a primary amine or a secondary amine, you would also get an intermediate analogous to this, but then it would also react further to give an imine or an enamine. So we've seen a number of different nucleophiles that react in this way. One of the biggest differences that we need to keep in mind when we have a very, very strong base or nucleophile such as a Grignard reagent, this reaction is irreversible. So this should not be an equilibrium arrow. When we have other nucleophiles such as cyanide or an alcohol or an amine, those are reversible reactions. When we talked about the reversible nucleophilic addition reactions, we saw that in general they worked better on aldehydes because they were faster and the equilibrium lied toward the nucleophilic addition product, whereas for most ketones the reaction is slow and the equilibrium lies toward the ketone, not toward the addition product. So just a few things that we need to keep in mind as we look at a new type of nucleophile that can engage in nucleophilic addition. So here we have a few examples of aldehydes, and we want to see if they can undergo nucleophilic addition. So if we start out with propanal and we treat this with hydroxide, remember this can do direct nucleophilic addition, which would lead to a hydrate, but then that is at equilibrium, and so eventually what can happen is that this can grab off one of these protons, and that will lead to formation of this enolate. Now keep in mind this is called an enolate because there is another resonance structure that can be drawn like this. And even though this structure would contribute more to the hybrid, it's helpful to think of it this way because this is how it reacts. Again, notice this was an equilibrium arrow. Here, this is a resonance arrow. So I'm going to focus on this representation of the enolate. Keep in mind, when we think about the position of equilibrium, we have the aldehyde plus hydroxide in equilibrium with the enolate plus water. And comparing the pKa values, we know that we have lots of unreacted aldehyde and a significant amount of enolate. So it's quite likely for a molecule of enolate to bump into a molecule of aldehyde and they can react. Because this is our nucleophile and this is our electrophile. So when this carbon shares its electrons with the carbonyl carbon, that will push these electrons up onto the oxygen. So what we get, we have the CH3, CH2, CHO minus connected to the CH, C double bond O, H, and remember this CH is still connected to the CH3. So this part of the molecule is what used to be the enolate that acted as the nucleophile, and this part of the molecule comes from the aldehyde that acted as the electrophile. From here, the O- can grab off a proton from the solvent, and that will lead to the product that looks like this. This is called the aldol addition because we end up with an aldehyde and an alcohol. It is effectively two equivalents of the aldehyde, one of which served as the nucleophile, the enolate, and one served as the electrophile, the aldehyde. While the original equilibrium step was not favored, and so we had more aldehyde than we had enolate, nucleophilic addition to an aldehyde is favorable, so that this equilibrium step is favorable. It lies toward the product, and then this step is also favorable and lies toward the product. If we look at our next example, if we have benzaldehyde and we treat this with base, well, there is no alpha hydrogen, so no enolate can be formed, and so there would be no aldol reaction. If we look at our third example, we can see that we do have alpha hydrogens, so hydroxide can grab off a proton from here, generating some of this enolate. I'm going to write out a little bit more. This enolate can now act as a nucleophile, share its electrons with the unreacted aldehyde, and that will lead to some of this, and then this can grab off a proton. Let's see, our solvent this time is ethanol. So the O- can grab off a proton from ethanol, and we will end up with this product. So one equivalent is the enolate that acted as the nucleophile, and the other equivalent is the aldehyde that acted as the electrophile. So what we have in the first and the third example, these are aldol self-additions because it's an aldol addition and we get an aldehyde and an alcohol. aldehyde and alcohol, and it's self-addition because the one compound formed an enolate, and that enolate reacted with another one of the original compound. So here we have aldol self-addition. Just to recap one of the examples from the previous slide, we had propanal can form this aldol product. Well, this aldol product, if treated with base or acid and heated up, this can be driven to lose water to form this alkene. And so we lose a hydrogen and an OH. Notice we specifically lose the hydrogen from the position alpha to the carbonyl because that gives us an alkene that is conjugated to the carbonyl, right? If we lost H and OH from here, then this would be an isolated alkene, an isolated carbonyl. But losing an H and OH here, that gives us the conjugated system. How does this work under basic conditions? Well, hydroxide can grab off the alpha hydrogen, and that will lead to some of this. So we form this enolate, and then these electrons can fold in here to form the double bond, pushing away hydroxide. We know that we have hydroxide present in solution, and so kicking out hydroxide is a reasonable occurrence. So that will give us, now the CH is double bonded to the C, still connected to the CH3, connected to the C double bond O. So this is an alpha beta unsaturated aldehyde. An alpha beta unsaturated aldehyde. What if we try to carry out the dehydration under acidic conditions? Well, here the oxygen would have to grab the proton first, and we would get the protonated alcohol. And this is when I'm wishing I used a smaller structure. Water can leave, and we generate a carbocation. And then water can act as a base, grab off this proton, allow these electrons to fold in here to relieve the carbocation. Giving us this product. So an aldol product can undergo dehydration either under basic conditions or acidic conditions. But keep in mind, the aldol reaction itself occurred under basic conditions. So let's focus on dehydration under basic conditions as well. Here's another example. If we have acetaldehyde and we treat it with hydroxide, this can grab off one of these protons, forming the enolate, and then this carbon will act as a nucleophile, share its electrons here, push those electrons up there, and then when that O- is going to grab off a proton from water, what we end up with looks like this. Okay, I wanted to take a shortcut, but I recommend you still write out the product after each step so that you get the practice seeing what's happening. On the previous slide, we said that we could take this product and heat it up in the presence of hydroxide. So that doesn't mean we have to carry out the aldol addition, isolate and purify our product, characterize it, get an NMR, and then we can set up another reaction. Instead, what we can do is carry out the aldol reaction under heat. What this gives us instead, well, as an intermediate, we make the same aldol product And then this aldol product, because there's still hydroxide present and there's heat, this will lose water to form this. So the first example, this is called the aldol addition product, or just the aldol product. And the overall reaction is called the aldol addition. In the second example, where the aldol product is formed and then dehydrated to give the alpha beta unsaturated aldehyde, this overall reaction is called the aldol condensation. A condensation involves the coming together of two compounds into one with the expulsion of a smaller compound. Two molecules add together with the loss of water. So whenever we have an aldehyde that can form an enolate, when it's treated with base but mild conditions, so room temperature or maybe even cold, then this will undergo the aldol addition so that you can isolate the aldol product. If we have the aldehyde that can generate an enolate and it's treated with hydroxide and heat, now it's going to go a step further. The aldol addition product is an intermediate, but the final product will be the condensation product, which is an alpha beta unsaturated aldehyde. So same conditions except for the addition of heat. Now what about ketones? If we have a ketone and we treat it with hydroxide and water, and so we stick with mild conditions, this can form some of the enolates. And then the enolate can add to the carbonyl carbon so that we will make some of this intermediate. And then this can get protonated by the solvent to give this. But remember that an acid-base reaction between an aldehyde or a ketone with hydroxide, this equilibrium lies toward the starting material. That's okay, that was overcome in the case of aldehydes. But with a ketone, the nucleophilic addition to a ketone is also not favorable. So this equilibrium lies toward the starting materials. The fact that this is an unfavorable equilibrium, that means that you are going to isolate very little addition product. However, if you do carry this reaction out under heat, all of these equilibrium steps are not favorable until you get to the loss of water, and you would be able to make this in fairly good yield. So for ketones, the aldol addition product doesn't work very well, but the aldol condensation can occur. Here's one more quick example. So from here we can generate this enolate, and this enolate can share its electrons here, leading to this aldol product, and leading to that. So because of the unfavorable equilibrium, this can be obtained in maybe about 20% yield. But if the reaction is carried out with heat, then that is going to bring us to this product, our alpha beta unsaturated ketone, and this can be isolated in over 90% yield. So it's really playing with equilibria that can lead to differences in reactions. So in general, aldol addition or aldol condensation. For an aldehyde, they can undergo self-addition as long as they can form an enolate. And aldol addition will occur under mild temperature. Aldol condensation will occur at higher temperature. For a ketone, aldol addition is not favorable, but aldol condensation does work.